Welcome to the Deep Dive. We're the show that cuts through the noise, digs into the sources, and, well, pulls out the insights you actually need. Think of it as your shortcut to getting properly informed.
That's the plan.
And today, we are tackling a really foundational document. It might sound a bit dry, Bitcoin, a peer-to-peer electronic cash system. But this white paper, it basically kicked off a revolution.
It really did. Published back in 2008 by, the still mysterious Satoshi Nakamoto. It's more than just a technical paper. It's the blueprint for a whole new way of thinking about money online. A cornerstone, really.
Absolutely. So our mission today is to unpack the genius in this thing. We want to get into the problems Satoshi was trying to solve. Look at the really clever mechanisms proposed.
Their core ideas, yeah.
Exactly. And pull out what makes it so revolutionary. By the end of this, you'll have a much clearer picture of, well, a pretty pivotal moment in tech and finance history. Ready to jump in?
Let's do it. So to really get why this paper was such a big deal, you have to remember what online payments were like around 2008.
Right. If you wanted to send money over the internet.
You pretty much had to go through what the paper calls a trusted third party. Like a bank, PayPal, that sort of thing. They were the gatekeepers.
And the white paper really drills down into the problems with that, doesn't it?
Yeah.
It talks about the inherent weaknesses of the trust-based model.
Mm-hmm. Big weaknesses. Like, you couldn't have truly final transactions. Disputes meant payments could be reversed by that third party.
Which sounds good, maybe, but it adds complexity and cost.
Exactly. And those costs, the paper points out, made small casual payments kind of impractical. Plus, merchants were always worried about fraud, right? They just had to accept a certain level of it as, well, the cost of doing business online, it wasn't ideal.
It's a stark contrast to just handing someone cash, isn't it?
Totally. You give someone a 20, it's done. Instant, final. No bank needed, no trust beyond checking the bill itself. But online, that just didn't exist. You always needed that middleman.
And that's the core problem Satoshi sets out to fix. The paper literally calls for an electronic payment system based on cryptographic proof instead of trust.
Allowing two people, just directly transact, peer-to-peer. It wasn't just about making things cheaper. It was about building something fundamentally different. Censorship-resistant, no central control.
Okay, so that leads to the big technical challenge. How do you stop people from spending the same digital money, twice the double spend problem, without a central authority watching over everything?
Right. So the paper defines an electronic coin not as a file, but as a chain of digital signatures. Think of it like a log entry.
Okay.
Each time the coin changes hands, the owner digitally signs a hash, a kind of cryptographic fingerprint of the previous transaction, and the next owner's public key. So you have this verifiable chain of ownership.
That makes sense for proving who owns it now.
Right.
But, yeah, how does the person receiving it know the previous owner didn't also send that exact same coin to someone else just moments before?
That's the million-dollar question. The double spend. And yeah, traditionally the answer was simple. Have a central mint or bank check every single transaction.
But Satoshi didn't want that. The paper argues that makes the whole system dependent on one company, just like a bank. It's a single point of failure, a single point of control.
Exactly. So Bitcoin's solution was, ingenious. It basically said, okay, all transactions must be publicly announced. Shout it out to everyone.
To the whole network.
Yeah. And then the network participants themselves need to agree on a single history, a single order of events, without any central coordinator. The person getting paid needs proof that the majority of the network saw their transaction as the first one for that coin.
Getting a whole bunch of random computers all over the world to agree on one history? That sounds incredibly difficult. How do you achieve that consensus?
This is where the timestamp server concept comes in. The paper suggests taking a bunch of recent transactions, a block, hashing them all together, and then publishing that hash widely.
Like putting a timestamp on it, proving those transactions existed at that moment. The paper even mentions publishing it in a newspaper or Usenet.
Yeah, conceptually.
Yeah.
And the really clever bit is that each new timestamp, each new block's hash, actually includes the hash of the previous block.
So it creates a chain, like linking pages in a book.
Exactly, a chain.
Yeah.
So if you try to tamper with an old block, you break the hash. You'd have to recalculate the hash of that block and then every single block that came after it because they all refer back. It makes tampering incredibly hard.
Okay, but how do you do that timestamping in a distributed way without one central server stamping things?
That's where proof of work enters the picture. It's inspired by ideas like Adam Back's hash cache. This is really the core mechanism.
Proof of work. Okay, explain that. This is the mining part people hear about, right?
Essentially, yes. Nodes on the network miners take the block of transactions they've collected, add a random number called a nonce, and then hash the whole thing using SHA-2526.
And they keep trying different nonces.
Over and over, billions of times a second. They're looking for a specific kind of hash output, one that starts with a certain number of 0 bits. The number of required zeros determines the difficulty.
Finding that specific hash is incredibly hard, computationally expensive.
Extremely hard. It takes a ton of processing power and electricity. But, and this is key, checking if a hash is correct is super easy. Anyone can just run the hash function once and see if it meets the target.
So hard to find, easy to verify.
Because it's so hard to find.
It means that once a block has a valid proof of work attached, it cannot be changed without redoing the work. And not just the work for that block, but for all the blocks after it in the chain.
Yeah.
It locks the history in place with computational power.
Wow. And this proof of work also solves another problem, doesn't it? How the network makes decisions.
Yes. It solves the issue of representation in majority decision-making.
Right.
You can't just have one IP address, one vote, because someone could spin up thousands of fake nodes, a Sybil attack.
But with proof of work, it becomes effectively one CPU, one vote. The collective decision-making power is represented by the total computing power participating. Nakamoto basically found a way to have a kind of democratic consensus in this completely trustless environment.
So the longest chain, the one with the most accumulated proof of work, is considered the valid one, because the majority of the honest computing power built it.
Precisely. As long as honest participants control more than half the CPU power, they'll consistently build the longest, most computationally expensive chain, outrunning any potential attackers trying to create an alternative history.
And the difficulty adjusts. How does that work?
The network automatically retargets the proof of work difficulty roughly every 2 weeks. The goal is to keep the average number of blocks per hour constant in Bitcoin's case, aiming for about 6 blocks per hour, or 1 every 10 minutes, regardless of how much computing power joins or leaves the network. It's like a built-in economic governor.
Okay, let's walk through how this all works in practice, step by step. Someone makes a transaction.
Right. Step 1. That new transaction gets broadcast out to, well, basically all the nodes it can reach on the network.
Like shouting it out, then.
Step 2. Each node collects these new transactions it hears about into a candidate block.
Get gathering them up.
Step 3. Each node starts grinding away, trying to find that difficult proof of work for its version of the block. The race is on.
Competing to solve the puzzle.
Step 4. When one node finds the solution, finds that winning hash, it broadcasts its completed block to everyone else. Eureka.
Step 5. The other nodes receive this new block. What do?
They check it quickly. Are all the transactions inside valid? Is the proof of work correct? Have these coins already been spent in an earlier block they know about? If it all checks out, they accept the block.
And step 6. How do they show acceptance?
This is the crucial part. They show acceptance by immediately starting to work on the next block, using the hash of the block they just accepted as the foundation for the new one. They build upon it.
Extending the chain.
Exactly. And the golden rule, as the paper states, is simple. Nodes always consider the longest chain to be the correct one.
What if 2 nodes find a block at almost the same time? You get temporary splits, right?
Yeah, temporary forks can happen. Some nodes might hear about block A first, others block B. They'll start building on whichever they saw first, but they'll usually keep the other one handy. As soon as someone finds the next block building on either A or B, that branch becomes longer, and the nodes that were on the shorter branch will switch over. The network converges back to one longest chain.
It sounds incredibly resilient. Messages can get dropped. Nodes can go offline.
And it mostly doesn't matter. Transactions just need to reach enough nodes to eventually get included. If a node misses a block, it'll realize when it sees the next one and can just ask a peer for the missing piece. It's designed for an unreliable network.
Okay, but why would anyone do all this? Run these nodes, burn electricity, finding hashes. What's the incentive?
The incentive structure. It's brilliant. The paper explains that by convention, the very first transaction in every new block is a special transaction.
A special how?
It creates brand new coins out of thin air, payable to the creator of that block. This is the block reward.
So that's how new Bitcoins are made. It's the reward for doing the work and securing the network.
Exactly. It's the main way coins were initially distributed since there's no central bank issuing them. The white paper uses that great analogy. It's like gold miners expending resources to add gold to circulation. Here, it's CPU cycles and electricity creating digital value.
Is that the only incentive?
No, there are also transaction fees.
Hmm.
If you send a transaction where the output value is slightly less than the input value, the difference is pocketed by the miner, who includes that transaction in their block. It's like a tip for processing the payment.
And the paper looks ahead, right?
Yeah.
To a time when the block rewards decrease.
Yeah, it outlines a long-term vision. The block reward is designed to halve periodically. Eventually, after a predetermined number of coins have entered circulation, about 21 million for Bitcoin, the block reward will become negligible. At that point, the incentive to secure the network can transition entirely to transaction fees and be completely inflation-free. The system is designed to sustain itself purely on usage fees eventually.
It even ties into honesty, doesn't it? The incentive structure itself encourages good behavior.
It does. The paper makes a game theory argument. Imagine a greedy attacker who somehow manages to get more CPU power than everyone else combined.
Okay, a nightmare scenario.
They could try to use that power to double spend their own transactions to defraud people. Or they could just use that massive computing power to mine honestly and collect all the block rewards and transaction fees. The paper argues they ought to find it more profitable to play by the rules rather than attacking the system and potentially destroying the value of the coins they're trying to steal or have already accumulated.
Fascinating. So, the economic incentives align with network security. Okay, what about practicalities? Like, doesn't this chain of blocks get huge? All these transactions forever. Disk space must be an issue.
That's a valid concern. The white paper addresses it with something called a Merkle tree. It's a clever hashing technique.
How does it help?
Instead of putting every single transaction directly into the block header's hash, you hash the transactions in pairs, then hash those hashes, and so on, until you get a single root hash that represents all the transactions in the block. Only this root hash goes into the block header that gets chained together.
So it summarizes everything.
Exactly. It means you can later prune off the old, detailed transaction data to save space, while still keeping the block headers with their proof of work and the Merkle root. You can prove a transaction was in a block without needing the whole block's data forever. The paper calculated that the headers alone are tiny, about 80 bytes each. Even with a block every 10 minutes, that's only about 4.2 megabytes per year for just the headers. Storage wasn't seen as a long-term bottleneck.
Very efficient. What about verifying payments? Does everyone need to run a huge full node storing everything just to check if they got paid?
No, and that's important for usability. The paper describes simplified payment verification, or SPV.
How does SPV work?
An SPV client, like a wallet on your phone, only needs to download the block headers that light rate 4.2 milbeat per year chain. When it wants to check a specific transaction relevant to you, it asks the network for the Merkle branch connecting that transaction to its block header.
So it gets proof the transaction is included in a block within the longest chain.
Right. It doesn't verify every transaction itself, but it sees proof that the transaction is acknowledged by the network's strongest chain. The trade-off, the paper notes, is that it relies on the assumption that honest nodes control the network. If an attacker somehow overpowered the network with a longer fake chain, an SPV client could be fooled. So, for high-value stuff, businesses might still prefer a full node.
Makes sense. And handling real-world money stuff, like paying with a larger amount and getting change back.
The white paper covers that too. Transactions aren't just one input, one output. They can have multiple inputs and outputs.
Yeah.
So you could combine inputs from several previous transactions you received and then create two outputs. One paying the recipient and another sending the change back to a new address you control. It's flexible, just like using physical cash.
Lastly, privacy. This is all public, right? Every transaction announced.
Yeah.
How is that private?
It's pseudo-anonymous, not fully anonymous. The privacy comes from keeping public keys anonymous. The network sees address A sent coins to address B, but it doesn't inherently know who controls address A or B.
Like seeing trades on a stock exchange without knowing the traders' names.
Exactly the analogy used in the paper. To enhance this, it recommends using a new key pair for each transaction, so it's harder to link different payments to the same person.
But there are limits.
Yes. The paper acknowledges that multi-input transactions, where you combine coins from several addresses to make one payment, necessarily reveal that all those input addresses belong to the same owner. So it's not perfect privacy, but a significant layer compared to traditional systems where your identity is directly tied to your account.
Okay, so we have this complex system. How secure is it, really? Can attackers break it? The paper actually tries to quantify this, right?
It does, which is one of its strengths. It clarifies what an attacker can't do. They can't just create coins from nothing, except through mining, and they can't steal coins from addresses they don't control the private keys for.
So what can they try to do?
The main attack considered is the double spend. Trying to reverse one of their own recent transactions. Say they buy something, get the goods, and then try to create an alternative blockchain branch where that payment never happened, sending the coins back to themselves instead.
The race between the honest chain and the attacker's secret chain.
Exactly. The paper models this race using probability theory concepts like the binomial random walk and the gambler's ruin problem. It's a bit technical, but the conclusion is powerful.
Which is?
The probability of an attacker catching up diminishes exponentially as subsequent blocks are added to the transaction by the honest network. Each block added on top makes it exponentially harder for the attacker to rewrite history.
So time equals security.
Pretty much. The paper then asks the practical question. How many blocks deep does a transaction need to be? How many confirmations before a recipient can be reasonably sure it won't be reversed? It uses Z for the number of confirmations.
And it gives actual numbers.
Yes, based on the attacker's assumed share of the total network hash power. For instance, if an attacker has 10% of the CPU power, Q0.1, after just 5 blocks are added on top, the chance they can successfully reverse the transaction drops below 0.1%.
Wow, pretty secure, pretty fast, assuming the attacker isn't too powerful.
Right. If the attacker somehow controlled 30% of the network power, Q equals 0.3, you'd want to wait longer, maybe for 24 blocks, C24, to get that same sub 0.1% level of certainty. It provides a concrete way to assess risk based on confirmations. It shows how cryptographic proof and probability can replace the need for a trusted intermediary. That's the breakthrough.
It really is an incredible piece of work when you lay it all out. We've gone from the problem of trust in online payments.
Through digital signatures, public announcements, the whole peer-to-peer consensus mechanism driven by proof of work.
Creating this immutable public ledger, incentivizing participation, handling efficiency, privacy concerns.
And even mathematically demonstrating the security against attacks. It's a remarkably complete vision laid out in just 9 pages.
The system's elegance lies in that simplicity almost. Nodes working together without needing much coordination, anyone can join or leave, and everyone just follows the longest proofs of work chain.
A decentralized marvel, really.
And it ends with this powerful idea. Nodes vote with their CPU power, expressing their acceptance of valid blocks by working on extending them, and rejecting invalid blocks by refusing to work on them. So I guess the final thought to leave you with is, what does it mean for our understanding of money? A value of trust itself, when consensus isn't dictated by an authority but emerges from computational work and collective agreement. How does that change things?